Len said that that he contributed a lot to, he can take all the credit for Vijay's eventual success because he gave him this advice to come and work with Manuel. If transitivity works on that, then you may be able to claim quite a bit of my success too, because then Vijay passed on that message to me, and so I. Oh, okay. Okay, great. So what I'll talk about is, after hearing the talks in this first session, I was telling Len that it seems to me by contrast, I'm going to speak about very conventional, very very sort of ordinary computer science, quantum computing. What I'll talk about is joint work with Zvika Brekersky, Paul Cristiano, Urmila Mahadev. Both of whom were are students of mine, and Thomas Vidic, who is a former student. And actually, I should say that Vijay and I have collaborated a lot, and it's been quite special because we collaborated actually starting I guess even before I started my PhD, maybe even quite a long time before I started my PhD. We started collaborating, and it's actually been quite quite remarkable. And once I started working on quantum computing, we collaborated much less. Although even after that, we did work on this Google AdWords problem. Vijay actually discovered the things that he really cares about very early in life. You can see examples of that. Okay, okay. So let me sort of say what what I want to talk about. Actually, it was exactly 25 years ago at this venue that Ethan Bernstein talked about the fact that quantum computers violate the extended Church-Turing thesis, right? Since that's something that we all build our entire that's the foundation that we build on. That really got people thinking, and actually it was this community, Simon Shore, lots of other people who sort of built up the foundations of this field within the next 2 or 3 years. Now, where are we today? Well, we're actually on the threshold of a practical demonstration of a violation of extended Church-Turing thesis. Okay. So Google, the Google UCSB team is actually planning to do their first experiments on this later this year. Okay. Since experimental violation of extended Church-Turing thesis is quite a mouthful, John Preskill, he coined a term for this, quantum supremacy. That was back in 2012. He could not have foreseen what would come later in 2016. And so, it was a very poor, in retrospect, not a very good choice of terminology. And so then in 2016, there was a bit of a flame war, how could you possibly call it supremacy and so on. So one of the big open questions in this area is there anything else you can call this that's not a mouthful? Okay, but what quantum supremacy is a practical quantum computation that is prohibitively hard for classical computers. Okay, and so why do we want? Why is it so important? Well, first of all, because it's a milestone, right? If you can't even, just as the violation of the extended Church-Turing thesis was initially shown by way of completely useless problems, challenge problems, which quantum computers could solve much faster than classical computers. In the same way, quantum supremacy says, look, forget about being useful for anything. Just show us that there's something that you can solve much faster on a quantum computer in practice than you could possibly solve using classical computers. Right? So it's obviously a milestone on the way. It's also sort of it's also proof of concept in the sense that you could worry about a lot of things about quantum computers. You could worry that errors are going to be overwhelming, right? Maybe errors don't scale the way we think they do. There are skeptics who would say, well, quantum computers won't work for some reason. We can't quite articulate why, but deeply we feel it shouldn't work, right? So if you have a demonstration of quantum supremacy, it lays all that to rest. But there's another reason to think about quantum supremacy, which goes well beyond this, which is it's a test of quantum mechanics. Okay, so this is not something you can say, well, certainly it was not something you could say in polite company in physics a decade ago. I finally worked up the courage to talk about this publicly in 2007 in a workshop that I think, it was the Lens workshops, which I played a role in organizing those. This was at Caltech. Okay, but in a CS audience, and now you can you can actually maybe mention these things, but in a CS audience we can definitely talk about it. So why would you want to test quantum physics? Well, you could say that this exponential growth, the fact that the power of a quantum computer or the size of the Hilbert space scales exponentially in the number of qubits, this is probably, at least from our viewpoint, it's the most counterintuitive aspect of quantum mechanics. And it also provides a limit in which to test quantum mechanics. Okay, so in the past, whenever quantum mechanics has been tested in a limit, like high energy or Planck scale, very small sizes or very, very large velocities, then something interesting has happened. Something new has been discovered. And so this provides another limit in which to test physics, which is high complexity. And the feeling is it's not going to break. Everything's going to be fine. But it's worth testing anyway, right? Because that's what one should do as a scientist. Okay, so let me just say what the Google UCSB proposal is. It's really to, since what they can do is they can create quantum circuits, superconducting quantum circuits, and they have, what they have done recently is synthesized a chip of 49 qubits, and once they calibrate them, they want to run these experiments where they would hook, where they would use these quantum circuits. Well, they can set up the circuit the way they want, whichever sequence of gates. So they want to hook it up as a random quantum circuit of depth about 50 as well. So 50 qubits, depth about 50, and they want to just measure the output and see what they get. Okay, so now how do they know that whether this really worked? For that, they need two things. One is they want to say, you could not possibly classically do this. Secondly, this is something they need to verify, right? So for all they knew, they implemented their quantum circuit, and it output just complete garbage, which was completely independent of the circuit they were trying to simulate. How did they know, right? So they have to test it against something and say, it really did output according to the distribution that the quantum circuit would have if it was properly implemented. Okay? So there are two tasks that they need to do. So how do they test that they actually got the probabilities right? Well, so what they plan to do is 50, because 50 is small enough that they can actually, given an x that was output, they can compute what's the probability of x under that quantum circuit using a supercomputer. So if you just stretch the supercomputer out as long as possible, you can actually compute these probabilities. And then they want to sort of do some sort of a test to see whether the more likely strings got output rather than the less likely, and that would be some sort of okay. So they have some score function. Okay, so now in order to of course it takes some work to actually show that this is a sensible proposal, and some work has been done to show that it's a sensible proposal, but that's not what I want to talk about. What I want to talk about is this 50, right? So, okay, so the reason behind the 50 is, the thought is 50 is large enough that, you would sort of say it's a coincidence if it all works out with 50. It's small enough that a supercomputer can simulate it, and so hence 50. But what if you really wanted to test for arbitrary n? How would you do it? Okay, so that's what I want to talk about. Okay, so the problem, it was implicit in everything I said. The problem is quantum devices are powerful, they're exponentially powerful. We need to, if you have to verify them, that's hard because we are not as powerful as them. Well, at 50, maybe with a supercomputer, but okay. And they're also fragile. Yeah. You could do that, but the point is that this is something that I skipped over, but let me just say it. So for the foreseeable future, we are not going to have quantum computers that can do that. So where we are is in this regime that's called NISQ, noisy intermediate scale quantum computers. And for different estimates, but if you wanted to factor, it might take maybe 10 years, maybe 20. We don't know. There you need error correction, fault tolerance. You need by the time you get there, you need millions of qubits. And okay, so that's just not going to work. Okay, so the problems are, the device is powerful, it's also fragile, right? Fragile in the sense that there's a superposition, but even as soon as you look at it, it goes away, right? So if you want to test and you want to look inside and see what's going on, that's just not going to do it because you can either have the computation or you can look inside, but not both. Okay, so the assumption that I'm going to work under, this question has been studied from various viewpoints, but I'm going to look at it in a new model. The new model is a quantum computer is polynomial time bounded. Okay, and I'll assume that the verifier uses post-quantum cryptography that the quantum computer cannot break. Okay, post-quantum cryptography, okay, this is, for those of you who don't know, there's NIST had a call for post-quantum cryptography proposals last year. The leading one is learning with errors. It's based on lattices. And the plan is that within the next few years, we'll move from RSA to this post-quantum cryptography. This is classical cryptography that you can implement today, but even a quantum computer won't be able to break. Okay, so I'm going to assume we have that kind of cryptography. As a verifier, we have that kind of cryptography. And the verifier actually also has a trapdoor and can check answers. So we want to restore some sense of symmetry between the verifier and this quantum device. Okay? Okay, so now what I want to do is describe to you a primitive. And this was supposed to be a general talk, and I'm hoping that this primitive is simple enough that it's actually a general primitive. Okay, so let me see if I can describe this to you. So the proposal for supremacy is like this. Okay, so the classical verifier sends across some function. This is your classical this is the classical cryptography. So F is being sent across to to the quantum computer. The quantum computer then sends back a string y. Then the verifier issues a challenge 0 or 1. And the computer answers with either a string R0 or a string R1. And then the verifier checks. Okay? And the claim is that if this checks out a few times, then you can be quite confident that the computer either broke your post-quantum crypto system or it's really quantum. Okay? So how does this argument work? It's somewhat reminiscent of zero knowledge, okay? Except that there's no secret that the computer has, right? So what we said is that the quantum computer really cannot break this crypto system. It's a classical crypto system, right? But it's post-quantum, so the computer doesn't really have any way of breaking the crypto system. And yet, whatever it's going to provide as an answer is going to show us that this was really a quantum computer. Okay, so how does this argument work? Well, it works like this. What we are going to guarantee is that no polynomial time classical or quantum computer can compute both R0 and R1, both the challenges. Okay? Okay, but so far everything is symmetric between classical and quantum. So why does this rule out classical? Well, because you see, if you look at the classical computer after y was sent to the verifier, okay, then what we can do is, after the challenge is issued and the computer responds, we can always reset the computer to whatever state it was in when it committed to y. Okay, and then send it the opposite challenge. And so if it's capable of answering both challenges, right? If it promises to answer you regardless of which challenge you give it, then it's going to be able to send you answer both challenges, which breaks the breaks the crypto system, right? Okay, so now the interesting thing is that the quantum computer can easily meet either challenge, not both, either. Okay? And so that's why this constitutes a proof of quantum supremacy. Okay, so let me try to explain this a little further. Yes?
Why do you need to choose the first quantum? Your goal is to prove quantum supremacy. Why do you need the first quantum crypto? Either you've broken the crypto system, which presumably is only possible with a quantum computer, or you're able to answer this challenge, both challenges which you gave.
Well, because we want a primitive that can do even more than this. So this is a building block which we'll use for even more things. Yeah. But good point. Okay, so what kind of crypto do we use? Well, we use a trapdoor claw-free function to gain this leverage. So what's this trapdoor claw-free function? I'll just give you a simplified version of it. It's a function that's 2 to 1. Right? And it's very hard to find two strings that map to the same thing. Okay? Actually, heuristically, I'll assume that it's actually very hard to sort of find any information about the two preimages together. Okay, that's how you should really think about it. It's also it's a trapdoor claw-free, meaning that once you have the trapdoor, then you can invert. So given a string y in the range of the function, you can actually find the two strings x and y which map to y. Sorry, x0 and x1 which both map to y. Okay, so there's an implementation of these trapdoor claw-free functions based on learning with errors and which have nice properties, all the nice properties we want. Okay, so now what is it that the quantum computer can do that we could not do classically? Well, quantumly, what we can do is we can sample a random element from the range of the function, and, okay, so we can sample a random y, output it, and then we can also be in a superposition over the two pre-images. Okay, so now what does this allow us to do? Well, we could measure the pre-image, and then we'll get either x0 or we'll get x1, each with probability half. Okay. So far, this looks completely useless, right? Because if you get x0 and y such that f of x0 equal to y, what did you get? You got a random x0 and f of x0. You could have done it yourself, right? In the opposite order. You could have taken x0 at random and then computed f and gotten x0 and y. Okay, so there's a second thing you can do. The second thing you can do is you can measure these qubits in a different basis. So you can perform a Hadamard transform on each qubit and then do a measurement. What this gives us is a random D, random string D, such that D times x0 plus x1 equal to 0. x0 plus x1 meaning the bitwise sum of x0 and x1. So what we get is an equation, right? You might remember this from Simon's algorithm, right? So you get an n-bit string D such that D gives you some information about x0 and x1 together. And this is not information we know how to get classically. Actually, for LWE, we can prove the following theorem using these. LWE has lots of very nice properties. There's these lossy techniques for proving hardcore bits. So what we can do is we can show that D times x0 plus x1 is a hardcore bit in the following sense, that if you can find x0 or x1, one of the pre-images, and a D, such that you have a better than 50-50 chance of guessing D times x0 plus x1. So if you can do this, then you can break the crypto system. Right? So that shows us that it's hard to output both x0 as well as D. Right? So now we are in the situation where, okay, so this is the protocol. We send over f. F is a description of this trapdoor 2-to-1 function, claw-free function. The quantum computer goes into a superposition. It sends you back y. You send a challenge, 0, 1. It does a measurement either in the standard or Hadamard basis. It sends you back either one of the pre-images or this equation. Okay. Now, you have the trapdoor, so you can figure out what x0 and x1 are, so you can figure out that the computer is honestly giving you the correct answer, either pre-image or an equation which, D times x0 plus x1 equal to 0. Okay. Okay. And we know that since the classical prover can be rewound, and it's impossible to hold both of these pieces of information, therefore no classical algorithm could possibly give you back this kind of information. Okay? So now we have, we are able to do this kind of verification of the supremacy, right? It doesn't matter what n is. Okay, but what kind of n do we need in order to make this happen? Well, if you use off-the-shelf LWE, then you would need a few hundred qubits to implement this, which is more than what Google can do today. It's 50 qubits and so on, 50 qubits, 50 steps. So one of the things worth doing is seeing whether one can meet in the middle in the sense, can you reduce this few hundred qubits? And well, the operations themselves, your classical computer can hold on to the matrix A, which is used in LWE, and the actual operations that you have to perform, are actually subset sums of some sort. And so the question is, how much can you whittle down on the number of qubits, and how much can Google or others who are trying to implement these NISQ quantum computers advance in terms of number of qubits and number of operations and so on, and noise, and can they meet in the middle? Okay, so that's as far as as far as the quantum supremacy goes. So now we can go a little further with this. Okay, and the little further means is this notion of certifiable quantum random number generators. Okay, so what's a certifiable quantum random number generator? It's something where you have a quantum device, you don't trust it, right? But what you want to do with it is you want to input a few random bits, and you want to get out a large number of random bits. Okay. Like a pseudo-random generator, except a pseudo-random generator only guarantees that the output is indistinguishable from random by a polynomial time machine, right? Computationally indistinguishable. What we want is that the output should be statistically random. It's the kind of randomness guaranteed to us by quantum mechanics. Okay, but also, in addition to guaranteeing that that output is random, we want a guarantee not on average, not well if the box is built well. What we want is a guarantee that even if the box was built by the adversary, who is who shares entanglement with it, that this particular output was random. Right? And this is something that that you can't do classically. Okay, so I'm just going to try to finish up in a couple of minutes. So the way you do it is you choose f pseudo-randomly. These are going to be the log n odd random bits that you send to the device. You use the 0 challenges to generate the randomness, and you throw in a few 1 challenges to keep the device honest. Okay? So you don't need too many bits to generate these 1 challenges, and you reap a lot of randomness out of it. So that's the way you get this expansion of randomness. And of course, there's this question, what we know is that d times x0 plus x1 is a hardcore bit. It's a computational randomness. How can we possibly claim that the output is statistically random? Right? We started off with computational randomness. How do we make this transition? And so this transition comes about where we show that the quantum device must be effectively measuring a qubit. So what we're going to do is we are, through this process, we are going to reach into the device and say, the only way the device can meet these challenges is if inside the device there was a qubit. It was initialized to 0. And when when the challenge is 1, the device measures this in the standard basis. If the challenge is 0, then the device measures this in the Hadamard basis, a 45-degree rotated basis. So it actually gets as output a truly random bit, a statistically random bit. Okay? And so, okay, so let me stop at the end of this slide maybe, or possibly after the, okay, so let me, so basically what this does is what we are saying is a qubit is defined by 2 anti-commuting measurements, those that make 45 degrees with respect to each other. These 2 measurements are uncorrelated, and this uncorrelation property we can somehow translate into anti-commuting measurements. Now, once we have this kind of a primitive, then actually this can be leveraged to do a lot more. And there's my student Urmila has her PhD thesis actually shows how to use these kinds of primitives to do quantum fully homomorphic encryption, which is how would you compute with a quantum computer on the cloud in such a way that the quantum computer learns nothing at all about your data? Or how do you even verify a general quantum computation. Okay, so I'll stop there.